These are examples for lesson 4.1 congruent triangles. In this video you will learn how to identify congruent polygons, especially congruent triangles, by the definition of congruency. Order is very important when working with congruent polygons. All corresponding angles and all corresponding sides must be named in a certain order. It's real easy when we have two polygons lined up right next to each other, where every pair of angles and every pair of sides match each other in corresponding places. For instance, A corresponds to S, so ABCD is congruent to STUV. Everything matches, it's in the same location, or the location that you would suspect it would be. Angle B corresponds to angle T, side BC corresponds to TU, and so forth. Angle D, angle V. But what happens when one of the figures, one of the polygons, has been turned, flipped, or a combination of it? In example 1, that's the sort of thing we have here. We've got this figure here is congruent to this one here. But it's harder to tell where each corresponding or matching part lines up. We can heavily rely on congruency statements like this one, because whatever's written here is in the order that these two are congruent. For instance, HI, side HI right here, is congruent, or is corresponding to side LM over here because it's listed in the first and second position of the name. So when figures are turned about like this can be really useful if you have the statement. So this is what they're asking us to do. If HIJK is congruent to LMNO, these quadrilaterals, what are the congruent corresponding parts? Remember, the parts of two polygons are either angles or the parts are sides. So starting with the congruent corresponding angles, we'll start with angle H. Angle H is congruent to its corresponding angle over in this other figure, and we know it's L because L comes first in the statement. So we come over to L and mark it with one arc. Then we go on to angle I. Angle I is congruent to angle M. M. Because it comes second in the listings of both quadrilaterals. Then we have angle J is congruent to angle N. And finally, angle K is congruent to angle O. It's in the last position of both statements. So writing these down, we have angle I congruent to angle M. Angle J is congruent to angle N. And angle K is congruent to angle O. Moving on to the corresponding sides, the first pair of sides we'll use is HI, like I mentioned in the previous sample. HI is congruent to, that's segment HI, congruent to segment LM. Be careful. If we were to write segment HI is congruent to segment ML, we would be incorrect. The order of the letters is extremely important when naming corresponding or matching congruent figures. So be careful there. Then we have these middle two, IJ, which would be here. This segment or side is congruent to NM or MN. MN. M comes first. So this side right here. So again, IJ is congruent to MN, side MN. Then next we have side JK, which are these last two. Put them come up here. Congruent to what? NO, right here. And finally, our last pair of corresponding sides that are congruent would be the first and last vertices that create a segment. HK, which is here, is congruent to LO, which is here. HK is congruent to not OL, but LO. We started with the first letter. Example 2, we can apply the definition of congruent angles or triangles to real-world problems. The wings of an SR-71 Blackbird aircraft suggest congruent triangles. You'll take a look at these two parts of its wing on either side, these two triangles here. They're congruent. And so we pull those out, and these are larger images of the two wings. See, that's E and F. And we've got angle B is 30 degrees, angle C is 75 degrees, and angle E is 30 degrees over in this other triangle. What is the measure of angle D? Well, we have to make sure everything matches up. It looks as though there's been some sort of reflection across a line in the middle of this aircraft. So that would mean A corresponds to D. So we could say triangle ABC is congruent to triangle, and we start with the vertex that seems to be reflected across this way, point D. D, and then we went up to B, and this one is reflected over. E would be next. F. F and C match or correspond. So we can use this, or we can continue to use the two drawings. But if the measure of angle D is what we're looking for, this one right here, that means we would need, using the triangle angle sum theorem, we would need another angle here. We could add it to 30, subtract from 180, and get this angle. Unfortunately, we don't have that angle. But if we come over here to its corresponding part, angle A, we already have these two angles here and here. So looking for the measure of angle A, we can use triangle angle sum theorem. And so that would be the measure of angle A plus 75 degrees plus 30 degrees equals 180 degrees. Then when you work that out, you have the measure of angle A plus 105 equals 180 degrees. Subtract 105 from both sides, the measure of angle A is equal to 75 degrees. So if the measure of angle A is 75 degrees also, then angle A and angle D, since they correspond, and write that right up here, angle A is congruent to angle D, then the measure of angle D is the same as the measure of angle A, 75 degrees. Since the two triangles are congruent, which angle in triangle ABC is congruent to the measure of angle D in triangle DEF? We just stated that D and A both correspond to each other, and since the two triangles are congruent, these two angles are congruent. So the measure of angle A. And this was by the definition of congruent triangles. We were able to find the measure of angle D, though, using the measure of angle A by the triangle angle sum theorem. Example 3. Using the definition of congruent triangles involves statements about each and every pair of corresponding parts of both triangles that you're working with. Are the triangles congruent? Justify your answers. Okay, here we have two triangles that have been produced. But one of them, it looks as though one of them has been rotated around this point right here. Point is, they aren't matching. They're not sitting next to each other in positions that allow us to easily see what matches with what. So if we take this triangle ABC and we just bring it down this way, where AC comes down to the ground level, so to speak, AC to here, and then we turn this one around, rotate it around this direction to where C now has been turned over to here, and E has been turned over to here, and D has been turned over up to here. Then we've got two triangles that are next to each other in a position where it's a lot easier to see what matches with what and what corresponds with what. So let's go ahead and write the congruent corresponding sides now. That would mean AB would be congruent to what? DE? No, it would be ED, because they have to correspond in their positions. A came first, so E comes first. Another pair, segment BC, or side BC, is congruent to what? That would be DC. And then finally, this side right down here, AC, side AC, would be congruent and corresponds to side EC. Congruent corresponding angles then would be angle A is congruent and corresponds to angle E. And notice angle B matches or corresponds with angle D, and so therefore they're congruent. Now, notice angle C. Angle C here is also angle C over here. It's just that this right here has been turned around. So this angle here, it corresponds and is congruent to this angle here. It used to be right here. And we know these are congruent by which theorem? The vertical angles congruence theorem, because these are vertical angles. So anyway, C moved, but it has the same letter when we moved it because of this situation here. Recall from the given diagram that the measure of angle BCA and the measure of angle DCE are, as we just said, vertical angles. So the last pair of congruent corresponding angles are, again, angle ACB, congruent to its corresponding angle ECD. See how they're in the same locations here and here. ECD. Look back up here. ACB, ECD. We started with A, and on the other triangle we started with E. And we ended with B on the first triangle and ended with D on the second one. So you have kind of a movement that does this. These two triangles are congruent, but in this order, like this. This was true, of course, by the vertical angles congruence theorem. Therefore, triangle ACB, make sure we get it in the right order, ACB is congruent to triangle what? A corresponds with E, C corresponds with C, and B corresponds with D, so that would be ECD. Triangle ECD. ECD. This is by the definition of congruent triangles. Each situation is a little different depending on what the triangle is doing with the other triangle. They could be overlapped. They could connect at one vertex like the previous example. So each situation is a little bit different. On to example 4, complete the proof. But first, what do you need to prove the two triangles below are congruent? All the parts are already marked for the given information, but let's go through them, each segment with each angle, so that we can figure out what we still need to show that the two triangles are congruent. This proof shows that if there were a way to shorten the process of this proving triangles congruent by using all these sides and angles, that would be to our benefit, or it could be, and that's what the next lesson is going to be about. So let's take a look at these two triangles. Notice that they both share a side together. Side LN is in both triangles, and you'll notice them over here when they want us to prove triangle LMN and triangle LON are congruent. LM, there's L, and there's L, there's N, and there's L, and there's another N. So they share that side. Well, in the given information, they say that LM, so it's right here, is congruent to LO. So LM, LO are congruent this way. And then MN is congruent to ON. MN is congruent to ON, like this. And angle M is congruent to angle O. Angle M and angle O are congruent across from each other, opposite each other. Finally, given to us is angle MLN. MLN, this one right here, is congruent to angle LON. No, that's incorrect. This would be, oops. This is not angle LON, it's angle. If this is MLN, it would be congruent to angle OLN. So correct that right there. So again, angle MLN, this one right here, congruent to angle OLN, this one right here. So there's been a reflection. These two angles. They give us all this information. If we didn't have it, we'd have to somehow show it. They want us to prove that triangle LMN is congruent to triangle LON. And as you can see, there's been a flip or reflection across this horizontal line segment LN. Okay, well, the first thing we can do is get the given information down, or part of it anyway. Let's take this statement and this statement. Let's take the segments first. LM is congruent to LO, these segments or sides, and side MN is congruent to side ON. This is all given to us. At that point, we would mark our sides with tick marks. Now, based on those sides, we have a third side in each triangle. So what do we do about this side that's being shared? Since this side is matching or corresponding to the same side in the other triangle, but it names itself, we write exactly that. LN, side LN in the first triangle, is congruent to side LN in the other triangle. L matches or corresponds with L in both triangles, and N matches or corresponds with N in both triangles. So we write LN is congruent to LN. Does this look familiar to you as a property? Recall the reflexive property. The reflexive property of congruence tells us that if you have a segment, an angle, segment A, number A, segment A, angle A, and it's congruent to itself, then that's the reflexive property. It's like looking in a mirror. So we actually use this property here to show that LN in one triangle is congruent to LN in the other triangle. They coincide with each other. One lays on top of the other. Well, now we've got all three pairs of sides, and we have two pairs of angles. We need one more angle. So let's get our angles, our given information for angles in here. We have angle M is congruent to angle O, And angle MLN is congruent to angle OLN. We changed it, or corrected it. This is given to us. Now, so at this point you would put your arcs on here, 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 and here. Again, we need one more angle. We just learned a theorem that says if two angles in one triangle are congruent to two angles in another triangle, then automatically the third angle in both those triangles has to be congruent. They have to be congruent to each other. So angle MNL and angle ONL have to be congruent. Angle MNL has to be congruent to angle ONL by the what? The third angles theorem. Now that we have all three pairs of angles and all three pairs of sides congruent, finally we can state that the two triangles are indeed congruent to each other. Triangle LMN is congruent to triangle LON. And that, because we had to show all 6 parts, that indicates that we used the definition of congruent triangles. Example 5. Once again, order is crucial when naming congruent triangles and using their parts too. So here we have triangle ABC is congruent to triangle DEF. The triangles are not lined up real nicely next to each other, so we're going to really pay close attention to our congruency statement here. Triangle A, or angle A, corresponds with angle D, and so forth. We're interested in sides AC and DF, so let's go ahead and label those so we can see exactly what we're doing. If they do correspond to each other, then we can set these two values equal to each other. If these don't correspond to each other, then there's nothing we can do. We won't be able to solve it. So taking a look at AC, AC's right here, that's 7A plus 5, and DF, which is right here, is 5A plus 9. Okay, again, just by looking at the diagram, it's a little harder to tell. So we come over here to AC in our congruency statement. It's the first and last letter, AC, starting with the first one. And DF is our first letter in the other triangle with the last letter. So are these corresponding or matching to each other, AC and DF? Yes, they are. AC is congruent to DF because the triangles are congruent. So if that's true, by the definition of congruent segments, their lengths are equal. And if their lengths are equal, the measures for those lengths are equal. So we substitute those in. 7A plus 5 equals the length of DF, 5A plus 9. Now we solve the equation and find A first. So subtract 5A from both sides, getting rid of the variable on one side. We have 2A plus 5 equals 9. Then we subtract 5 from both sides, and 2A equals 4. Divide both sides by 2, and A is equal to 2. We use this 2 to find what we're looking for. It says find the lengths of the given side. So we need to find AC, the length of this. AC is equal to 7 times 2, which is A, plus 5. Substitute that in. We get 14 plus 5, or 19. 19 is the length of AC. Now, if we're correct, our other length here for DF should be 19 also. Let's check it out and see. DF is equal to 5A plus 9. 5 times A, which is 2, plus 9. That gives us 10 plus 9, which is 19. And so DF is also 19.